So we're recording now, and I'm going to start off. There's a document that's on Blackboard under lab sections 003 and 004 under the folder for this session, March 24th. And on that folder are these 6 files, a link to this lecture and these 6 files. I'm going to start with the one that's labeled Part 1, Single Sample Test. 324, part 1. Okay, so I'm going to open that up in Word. It's a Word document. And we're going to go over some typical examples that will show you how you might see some problems presented to you that involve single sample tests. Single sample tests basically are situations when you're sampling a population and you're comparing it to a given number. For instance, let's say I know what the average cheese intake of Frenchmen are. They do extensive research in France on cheese, and we know exactly for the whole population what the average per capita consumption of cheese is. In the United States, we haven't done such a extensive survey, so we're forced to take a sample. So I'm going to take a sample of, say, 100 or 1,000 or 5,000 Americans and survey how much cheese that they consume. And I'm working with a sample and an estimate of the mean for the United States, but I'm comparing it to a known mean in France. So that's a single sample test. I'm comparing a sample to a known mean. So the problem is that whenever we get the mean of a sample, we don't really know the mean of the population for the United States. We only know the mean of the sample that we took. We know that the bigger the sample is, the more likely, the closer we are to what the mean of the population would be. Okay, so let me just turn down the sound here a little bit so I don't get some feedback. So we know what the mean of the population would be. Are we getting some feedback? My hearing is that from another room. It's from the hall? It's from the hall, or is it from the speaker here? There's something, right? How's that? Better?
It's
Coming from this machine?
No, it's like I can hear it.
It's not coming from here. Okay, I'll live with it. Okay, so at any rate, I'm looking at we know we know the population, we know the mean of one population. We're guessing at the mean of the other population. There's a couple of ways that we can determine whether or not we can say that there's a statistical difference between the two means of the two populations. We don't care if there's a difference between the mean of a sample and the mean of a population. We're using that sample mean to tell us as much as we can get about the population mean. That's what we really care about. So there's 2 ways that we can do that. One way is to use a confidence interval. If I have a sample and I find an average, I can then calculate based on the variability of the individuals in that sample. I can calculate a standard deviation, and then based on the sample size, I can calculate a standard error. So I know what the variability is, and I can calculate a 95% confidence interval. In other words, I know the mean of the sample, and I know a range within which I can say I'm 95% sure the real mean for that population lies. So now, if I'm comparing it to the other population, say France, I can look at that and say to myself, well, if France, they consume 50 pounds of cheese per year, and the United States, my sample consumed 35, but my 95% confidence interval was 30 to 40. Well, I'm 95% sure the real mean for the cheese consumption in the United States is between 30 and 40 pounds. So that means I'm also 95% sure that it's less than what they eat in France, because what they eat in France, I know, is a mean of 50, because I know the population mean for France. Now, if I had found that same result, a mean of 35, but there was a lot of variability, and it turns out my confidence interval was from 20 to 52, Well, now it's entirely possible within my 95% confidence level, it's entirely possible that the American mean could be 49, 32, 50, 50, 51, or 52. So I'm no longer sure that it's different than 50. That's why I'm so interested in the confidence interval. I want to make sure that my confidence interval doesn't include the number that I'm comparing it to, so I can say with at least 95% certainty that they're different. Okay, so that's what the confidence interval is all about. The t-test does this same thing in another way. The t-test measures the number of standard deviation apart that these two proposed means are. So I know that if I look at my sample mean and I look at the mean for Frenchmen, and I say to myself, well, gee, the mean that I got for my sample was 35. The mean for Frenchmen is 50. Well, the difference between those two is 15. And if I determine the standard error for my sample is 5, well, there's 3 standard deviations apart. And we know that anything more than 1.96 standard deviations apart means that there's less than 5% chance that the two means could be the same. So you can look at it that way too, from the perspective of a distribution and calculating a z-score for what the probability of those two means being from the same population, okay, or being part of the same population. There's a couple of ways that we could do that. Okay, so we're going to get a couple of examples of that, and hopefully when you see it actually worked out, it'll be clearer than it is for you right now. I know it's kind of a confusing concept, but when we actually apply it, I think it's going to make more sense. Oh, I see. Okay, somebody's unmuted. I'll go in there and do that right now. And why can't I find it? Mute all. That's what it was. There was a sound there in the background. Okay. Okay, so I'm going to I'm going to go ahead and work out this example. If you guys open it up at the same time. Okay, happens to be a hot time for basketball, so we're going to have a basketball example. Okay, but we want to examine if the number of fouls called in the regular season games is different than during the NCAA tournament. Okay, so the first thing we know is the season's over. So we know that during the entire season, there was an average of 40.1 fouls called per game. Okay, now in the playoff games, we sampled 64 games at random, and we found that the mean for those 64 games was 38.95 fouls per game. Well, that's less than 40.1. We know what the average is for the regular season because we have basically what is the entire population for the regular season. We have all the statistics for the regular seasons. We know every game and how many fouls were called. So this number is a population mean. This number is a sample mean because there have been more than 64 games played. Not that many, but there's more than 64 games played. Okay, so the standard deviation for that sample of 64 games is 5.8. So we know a standard deviation, and we know the sample size. So now this standard deviation is the standard deviation for the sample. Just like the mean, we believe that it approximates the standard deviation for the population, but we don't know that for sure. When we have sigma, if this were sigma, right, then we would use the z-table for certain. Because when we know sigma, the population standard deviation, in other words, standard deviation for the entire population, we can use the z-table with some confidence because we know exactly what the standard deviation for the entire population is. However, in this case, we don't know sigma. We only know standard deviation of our sample. So we instead will most likely use the t-test, the t-table. Okay, so we're relegated to using the t-table. Now, in many cases in the future, we're going to find out that if the sample size is larger than 30, many statisticians, not everybody, but many statisticians, will just go straight to the z-table because the z-values and the t-tables get closer and closer together as they get larger. Anybody remember when I told you that they're the same? Oh, somebody's getting way ahead of us there. Anybody remember when the Z score and the T score are exactly the same for a sample? How big does the sample size have to be for them to be exactly the same? Infinity, exactly right. Okay, so it's got to be an enormous number to be exactly the same. But once you get into very large sample sizes, and I'll demonstrate this to you, once you get into very large sample sizes, they get so close together. For a t-score for a 95% confidence interval might be for a couple of hundred, a sample size of 100 or 200 might be 2.0 instead of 1.96. So it gets close enough together that for practical purposes, very frequently you use the z-table. But let's go ahead and solve this particular problem. So there's two ways we're going to look at this. First, we're going to look at it in terms of it being a confidence interval problem, and then we're going to look at it in terms of being a hypothesis testing problem. So I'm going to pull up this pad, and I'm going to get started. And the mean of the population, the mean of the regular season, I'm going to mean R is equal to, what did I say, was 64? 40.1. Okay. Okay, and the mean X bar for our sample was 38.95. Okay, and our standard deviation for our sample, how much? 5.8. Okay, so let's calculate a confidence interval for this sample. So our confidence, first thing we need to do to calculate a confidence interval when we have samples, we have to calculate standard error. And normally, the standard error would be sigma over the square root of n. We don't know sigma, so we're going to have to use the standard deviation. Okay, it's going to be equal to approximately the standard deviation over the square root of the sample size. So that's going to be 5.8 divided by 8. Yes? No, standard deviation of the sample is the standard deviation of the sample. In other words, the standard deviation of the sample is calculated on the individuals in the sample that you have there, just like you would do it for the whole population. Remember when we did it, we took the difference between the mean and each individual value, and then we squared it, then we added them all together and divide by n minus 1 and found the square root, and so on and so forth, the variability in this. That's the standard deviation. The standard error is the standard deviation for repeated samples of the same size. In other words, what we're looking at now, this standard error is the variability for if we took repeated samples of size 64, what would those averages be? Not for anything to do with the population. So that's a much smaller number. That's why that square. When I'm talking about standard deviations for the sample, we're talking about individuals. When I'm talking about standard error, I'm talking about the standard deviation for sample means of that size. If you took it over, if you can imagine doing it over and over and over again. And that's why we divide by square root of n, because it makes that width much narrower. Because obviously if we're going to average 64 people together, we're not going to get low numbers and high numbers anymore like the individuals might be. We're going to get numbers in the middle, like people that don't eat any cheese and people eat 400 pounds a year of cheese. Okay, in this case, fouls and a basketball game. Okay, I didn't repeat that. I think you guys got the gist of that online, from the way we were talking. So our standard error is going to be 5.8 over 8. So I'm going to get my calculator out, and I'm going to calculate that. 5.8 divided by 8 equals 0.725. Okay, now I'm not going to round that. Let me get back over here. 0.725. I noticed this came up a lot in the homework. I'm not going to round that. I'm only going to start rounding when I get to the very end. I might, instead of working with 4 decimal places, I might work with less than, 4 or 5 or 6 decimal places. I might work with 4 or 5 or something like that. But I'm not going to round until I get to the very end. I'm about to show you why I don't want to round until I get to the very end. Okay, so now I want to calculate. I got my standard error. I got my mean. That's really all I need to calculate my confidence interval. So my confidence interval is going to be X bar plus or minus. Now I have to decide what this factor is going to be. Now, if I'm willing to use the Z table for a 95% confidence interval, what's that number going to be? 1.96, right? And I'm going to do it that way for a moment. It's going to be one because my sample size is pretty big. It's a sample size n is equal to 64. Pretty big sample size. Okay, 1.96 times my standard error, which is 0.725. Now, if I had rounded this 0.725 to 7.73, next thing I'm going to do is multiply it by 1.96 or almost 2. So I double my rounding error, right, by doing that. So that's why, and it's not so severe in this situation, but you'll find that in a lot of statistical calculations, you're taking numbers and you're repeatedly doing different operations on them. So if you start rounding in the middle of the game, by the time you get to the end, instead of like losing a digit, you lose several digits because you've rounded so much intermediary, and then you've multiplied and squared things and so on and so forth, and that's multiplied your error. Okay, so I'm going to multiply this by 1. Let me get my calculator out. Okay, and I'm going to give up this round. This is just a lesson so that we can get through this. Times 1.96, 1.96 is equal to 1.421. I'm going to put that into memory on here, and I'm going to clear this. So my confidence interval is going to be my mean, which was 38.95, 38.95, minus my 1.96 times 0.725, which happens to be in memory. So I'm going to recall it, and that's going to be equal to 37.529, 37.529, or 37. I'm going to now round that now, 37.53, comma, and the other end it's going to be, let me clear that, and it's going to be 38.95 plus what I put left in memory there is 40.371. 40.371. I'll round that to 0.37. That's my 95% confident interval. I'm 95% sure that the average number of fouls during the playoffs is between 37.5 and 40.4. What did I say that the average was for the season? Can I say that they're different with 95% confidence interval? No, I can't, because it's entirely possible that during the regular season, during the playoffs, that it is 40.1, because that's within my 95% confidence interval. If during the regular season it had been 40.4, that would be outside of this range. So now I could say with 95% certainty that my sample mean, the mean of my sample population, the mean for the whole population, which I believe is between this number and this number, is different than the mean for this other population, the regular season games. Do you guys get that online? I see a lot of you guys getting the same numbers as I am, so I'm happy about that. And you're agreeing with me that no, you can't say that they're different. Okay, so now I'm going to do this same problem, except I'm going to do it from another perspective. I'm going to do it from the perspective of hypothesis testing. Okay, let me start with another clean sheet. Oops, wrong direction. Okay, so I'm going to start off with we always start off hypothesis testing with a null and an alternative hypothesis. So H null and H alternative. Okay, so they have to be mutually exclusive. So you can't have something that's going to be satisfy both conditions. Almost always H null involves an equality of some kind. Okay, so in this case, our equality is that X bar, mu, or rather the mean during the playoffs is equal to the mean during the regular season. And our alternative hypothesis is going to be the mean during the playoffs and the mean during the regular season are not equal to one another. Okay, what kind of hypothesis is that? One-sided or two-sided? That's a two-sided hypothesis, because I'm not saying whether in advance that I'm accepting if I'm interested in whether the regular season and the playoffs are larger, whether during the playoffs there's fewer fouls or more fouls. I'm just saying there's a different number of fouls that take place during the playoffs. Okay, so this is a two-sided hypothesis. If I had wanted to make it a one-sided hypothesis, Maybe I want to argue that there's fewer fouls during the playoffs because they want to make it more entertaining, the game. So my null hypothesis would be mu during the playoffs, right, is less than or equal to mu during the regular season. Okay, and my alternative hypothesis is mu during the playoffs is greater than or equal to, and mu during the playoffs is less than mu during the regular season. Okay, so that these are mutually exclusive. If it turns out that there's more fouls during the playoffs or there's an equal number of fouls, I fail to reject my null hypothesis. My null hypothesis is true. If there are more fouls during the playoffs, it satisfies my alternative hypothesis. This is what I'm really trying to prove. This is my null state. In other words, what my situation is now, and this is what I'm trying to prove. I'm trying to reject this as being the truth and accept this as being the truth instead. This is a one-sided test. So in this kind of test, things get a little bit more complicated because in this kind of test, when I'm looking for a difference, let's say I'm willing to accept a 5% chance of error, right? 0.05 or 5% chance of error, right? That's the same thing as having a 95% confidence interval, right? Having 5% chance of error. Okay, so in that case, instead of setting up my range for my t-score so that one or my z-score, so it's negative 1.96 and plus 1.96, which accounts for a 2.5% chance of error at the high end and 2.5% of chance for error at the low end. In this case, I'm looking only at the low end. So in other words, I'm willing to put all 5% of chance of error down here and say to myself, there's no chance of error at the high end. It can only be lower, the number of fouls during playoffs. So that's a leap of faith to say that. So that's why usually we wind up doing two-sided tests anyway. So now, in order for that to work, I don't need Z or T to be 1.96. I'm perfectly happy with it being for 5% 1.64. In this case, negative 1.64. Right? So it's a lot less rigorous of a test. So let's do this as a two-sided test for right now. So let's see what we need to do here. Our Z score is going to be equal to X bar, X, the value of X that I have for my sample, minus mu over the standard error. Okay, so what is now, if I'm going to use T instead, I'm just going to say T is equal to X bar minus mu over the standard error. Same calculations, it's a question of what we're going to do with that number. Okay, so let's see what we get. X bar is X bar was 38.95 minus 40.1. Right? It's coming out, notice it's on the low end there, so it's coming out negative. Over the standard error, what was the standard error again? 0.725? Okay, so let's figure out what Z or what T is. By the way, I think that's the other room there. Guy's got a kind of a really grating voice, eh? Don't tell him I said that. Minus 40.1 equals divided by 0.725. Okay, so I get a Z score or a T score of, oops, I didn't want to do that too much, minus 1586. I forgot it already. 586. Okay, so that's my Z. If that's my Z score, how do I figure out whether I can reject the null hypothesis? What does my p-value have to be in order for me to reject my null hypothesis? Right? Right, that has to be less than 0.05. In order for me to reject the null hypothesis, p has to be less than alpha, which is 0.05. Okay, so let's look that number up on the Z table. Okay, so I'm going to go back to my Z table. I uploaded a Z table for you guys as well. So if I go to Agresti and I go to my Z table, I'm going to go minus 1.57, 1.59, 1.5, oops, I'm gonna have to move that over. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0.0559. I'm going to call it 0.056. Okay, so now what that's telling me is that on this side of the distribution, I have 5.6% is where my z-score winds up. I have 5.6% chance of being wrong on the low side. Since this is a two-tailed test and we started out with the assumption that we could be low on the high or the low end, we have to double that number because we have to account for the top part too. So that's 5.6%. So what's our total? If we wind up with a z-score of either negative or positive, 1.56, what's our chances of being wrong? Our chances of being wrong are 11.2%, or 5.6 twice. Everybody okay with that so far? So now, if it had come out to be, if our z-score had come out to be negative 1.96, and it had been over here, if I had gone to the table, what would this area have been? Would have been what percentage? 1.96? 2.5%, right? And we would have doubled that and it would have been exactly 5%. Okay, and don't dare ask me what do you do when it's exactly that 5%, because there's no right answer to that. Okay, and everybody asks that every semester. Okay, it's like so. At any rate, so are you speeding when you go 55, or are you going the speed limit? Yeah, are you? I don't know. Aren't you supposed to be under 55? Is it? Okay, never mind. It's the same kind of thing. Okay, so at any rate, had it been 1.96, we would have doubled it, and our p-value would have been 0.05. Our p-value here is, yeah, we don't need a negative for this, is 0.112. Okay, it's bigger than 0.05, so we fail to reject the null hypothesis. Okay, I'm justifying using the t-table because n was greater than 30. A lot of statisticians won't do that. Remember, n is 64 here. It's quite a bit bigger than 30. A lot of statisticians won't do that. A lot of statisticians will say, hey, don't do that because you're introducing error there. Why not just use the t-test? Okay, so now let's look at the difference here. It's really the same calculation. It's negative 1.586 and negative 1.586. Same number, right? We get the same number. The question is, what does that number tell you about the t-test? Okay, so now I'm going to open up the t-table. When I open up the t-table, because, let's see, let me get to the t-table here. Okay, here's t-table. Okay, so let's look at the t-table. First of all, there's a different value for the t-table scores for different sample sizes. When we were dealing with the z-table, the sample size didn't matter. There was only one z-table for all sample sizes, as long as we knew what the standard deviation of the population was. When we're dealing with the t-table, the sample size is critical. So if I'm looking here, my 95% confidence interval, in other words, my t-score, when there's a quarter of a half a percent, 2.5% on both ends of the distribution. This is the right tail probability, 0.025. Add the left tail to that, and you get your 5% or your 95% confidence interval, right? I need to go down to 64 for this. Well, there is no 64. The closest I can get is about 60. What is the t-score for 60? It's exactly 2.0. Had we had a sample size of 80, it would have been 1.99. Sample size of 100 would have been 1.98, right? And they don't even bother going above 100 with this table because it gets so close. It just gets closer and closer and closer and closer to 1.96, but it never reaches 1.96 until the sample size is infinity. So if we use the value 2.0 for t, instead, what we're saying that if the t-score is greater than 2, if the z-score is greater than 2, then the probability of being wrong is less than 5%. You're outside of your 95% confidence interval. If the t-score is less than 2, it means that you're not far enough away. You're not enough standard deviations apart. You say with 95% certainty or 5% chance of being wrong that the two means are really different. So what was the mean that we found here? The mean that we found, the t-score that we got, which represents the number of standard errors apart, is 1.586. I'll call it 1.6 for a moment. 1.586 is smaller than the t-score that we need to say that these two things are really different. Remember, had this been a z-score, it would have been 1.96. But now for a t-score, it's got to be 2.0. Had it been a sample size of 25, we would have had to exceed a t-score of 2.06. Had it been a size of 12, we would have had to exceed actually a sample size of 12 would be 11 degrees of freedom. We'd have to exceed a t-score of 2.2. So the smaller the sample size is, the larger the number that you need to exceed for your t-score in order to say that there's less than 5% chance of being wrong if you say the means are different, okay, or that they're not within, that one mean is not within the confidence interval of the other mean. Okay, so that's really what we're after here, is doing that. Anybody got a good name for what this t-score is for this particular sample size? What would be a good name for this t-score? Make one up. It's an important t-score. It's so important, this t-score, to whether or not we reject the null hypothesis, that nothing else means anything. This t-score is critical, right? You want to get BERT. We're not calling it BERT, no. The t-score is, some of you suggested we call it BERT. The t-score is called, this score is called t-critical. That's the value of t for that sample size that we need to exceed to reject the null hypothesis. So I'm going to go back to my hypothesis, right? The nice thing about assuming the z-score is that we can actually estimate a p-value, a probability of being wrong, if we reject the null hypothesis with this data. In other words, we got more than 11% chance of being wrong if we reject the null hypothesis. The t-test really only tells us if it's greater than or less than a 5% chance of being wrong. Okay, so in this case, our t-score is less than our t-critical, so we fail to reject the null hypothesis. So notice what I'm saying here. I fail to reject the idea that these two means are different. I don't say that the two means are the same, right? Because that's not what I proved. I just failed to reject the idea that they were different. So I failed to reject the null hypothesis. Had my t-score been bigger than 2, I could have said I reject the null hypothesis and I accept the alternative hypothesis that they're different. Did I get the same result as I did for the 95% confidence interval? Yes, I did. Remember, I said I can't say they're different based on the confidence interval. I also can't say that they're different based on the hypothesis testing. Okay, the best way to really understand this is by repetition, and if you need to in the beginning, using the formulas kind of as a crutch. Okay, so the next problem I'm going to do is going to be a little bit different. Okay, there's a little bit of a twist in the next problem. Same idea, little bit of a twist in the problem. If I can ever find it again. I think that's it. Is that it? No, that's not it. Where's Word? Here it is. Okay, next problem. In this case, I'm looking at a one-sided example. Are the number of fouls called in a regular season game higher than the NCAA tournament? Okay, so what are we doing here? In this case, we're looking at regular season game is 40.1. The playoff game is 38.5. The playoff games, we have sample size of 64 games. The mean is 38.5, same as before, except this time, as I mentioned before, our null is the average during the tournament is let's see, we want to argue that the regular season game is higher. Null during the tournament is less than regular season. During the tournament, it's greater than. Nope. What am I saying? Regular season. Our null is, it's great. Well, I'm going to do my alternative hypothesis first because that's easier. What I'm trying to prove is that during the tournament, that the average number of fouls is less than during the mean for the regular season. Okay, so what does that leave for my null hypothesis? Greater than or equal to the regular season. See how it was easier to really to do the alternative hypothesis first and then do all the other possible conditions for the null hypothesis, including equal, always includes equal, the null hypothesis. I'm arguing that during the regular season, there's more fouls than during the tournament. So my mean for the tournament is less than my mean for the regular season, right? Regular season's more, I'm arguing there's more fouls during the regular season. They call fewer during the tournament. No, that's what I'm trying to prove. Your alternative is always what you're trying to prove. In other words, you're trying to reject the null and accept the alternative hypothesis. That's what your proof is doing is it's assuming that what you're trying to prove is not true and forcing you to provide evidence that it is true so you can reject the null and accept the alternative hypothesis. So I want to prove that there's fewer fouls, less than during the regular season, fewer fouls going during the tournament. So my null is that during the tournament there's more or equal to. Remember, we just did the same problem with equals and does not equal. It was a two-sided test. So in this case, I'm going to calculate z or t, right? I'm going to change this to t, and we're going to use our t table instead. Okay, so we calculated this before. Anybody remember it was 1.58, right? 1.56. Okay, it's the same calculation, right? We didn't change any of the numbers, same calculation. The only thing we changed was the way that we're looking at the probabilities. So now I'm going to go over to my t table, and I'm going to look at my t table, except this time, the right tail probability, you can also look at that as this, since it's symmetrical, as the left tail probability. The right tail probability before was 0.025. In other words, 2.5% on the upper side, 2.5% on the lower side for a 95% confidence interval. Well, since we're willing to put all 5% on one end, on one tail, now we have a different number that we could use for the t-score, t-critical. So I'm going to go down to 60. What's t-critical now? It's 1.671. It's a lot easier to prove. All I have to do is exceed that number for a one-tailed test. So did I exceed that number? Not quite. Still same problem. I still failed to reject the null hypothesis because 1.56, my t-score, is still less than the critical value of t that I need. I came awfully close though, didn't I? A lot closer than before when it was a one-tailed two-tailed test. Two-tailed test almost always more rigorous than a one-tailed test. Okay, I see some blank faces there. Yes, questions? Let's take a look at this. One of the things that you can do is you can look at this and say to yourself, okay, now my 1.56 for a sample size of 60, I didn't succeed in rejecting the null hypothesis here. But look at this, in this other column, I do reject the null hypothesis, right? So my probability is somewhere between this value and this value. If I go to the top, this is for a one-tail probability of 5%. This is for a one-tail probability of 10%. So what this suggests is that the probability for this one-tail test is somewhere between 5 and 10%. Had it been, let's say my t-score had been 2.1 for a sample size of 60. 2.1 for a sample size of 60. Okay, 2.1, I would have rejected it here. I would have failed to reject it here. So for a two-sided test, okay, it would be, I'm going to go back to the top here, it would be between 5% and 10%. Oh, excuse me, between 5% and 2%. This is 98% confidence interval, 1% on each side, right? Or 2% total. This is 5%, this is 2%. So it would have been between 5 and 2%. So you can kind of use the t-tables to bracket what the real probability is, but it's not like using the z-table where you get an exact number. Okay, so this is pretty confusing, I know. And we're gonna look